Hi, this is Kevin Iga here with lectures on Calculus 3. So we have a midterm number 4, coming up next week, Tuesday, and we return to campus on Monday. So uh, we have a day while back to prepare. I'm going to have to ask, though, that you bring questions even before we come back. Text me, call me, email me, whatever. I hope to address your questions mostly before we get back. The idea is on Monday we actually have to cover some new material. I'm sorry to say, it's we're just at the end of the semester. We don't have a lot of leeway as to exactly how we're going to do things. So um, please um, try to get your questions answered before then. Pretend this test is coming up sooner than it really is. Um, then that makes your study habits come earlier. That way, you can ask questions early on. I will answer questions about the midterm, but I'm thinking that mostly we'll be covering new material on Monday. Okay. All right. There is a review sheet online, though. You should go to courses and go under resources. You'll see review mid 4. Okay, so that's a review for midterm number 4. It describes what topics are on the test. All right. So we're going to talk about div, grad, and curl today. Okay. Of these, grad, you've already run into gradient. Okay, that's the gradient. We actually have seen a number of different kinds of derivatives in this course. Okay, partial derivatives, directional derivatives, total differentials, and the gradient, the main examples. And now we're going to talk about two more kinds of derivative, the divergence and the curl. Now, the gradient, we take the gradient of a function. I call it a scalar field here. I haven't used that term before. What I mean is a vector field means at every point in the plane or in space, depending on whether we're doing a two-dimensional or three-dimensional problem. Well, at any one of those points, you're going to have a vector. That's called a vector field. Well, if at any one of those points you have a scalar, that is a number, that's what we mean by a function from R2 to R or R3 to R. Okay? And so that's called a scalar field. It's what we used to call a function. And the gradient is, you take the gradient of a scalar field, the result is a vector field. Now the divergence and curl, they are written like this. Okay, the divergence of a vector field will be a scalar field, and the curl of a vector field will be a vector field. So the divergence and the curl are notions of derivative that apply to vector fields. Let's review the gradient. Okay, this is a gradient of a function of two variables. This is a gradient for a function of three variables. If you have two variables, you just take the partial derivative of f with respect to x and with respect to y and put them together into a vector like this. Of course, for 3 dimensions, this partial derivative with respect to x, y, and z, and put it together into a three-dimensional vector like this. That's what the gradient is. What's the divergence? The divergence of a vector field. Okay, so I'm going to write down my vector field like this. It's got the first component is called P. The second component is going to be called Q. And if I have such a vector field, the divergence is you just take the partial derivative of this with respect to x plus the partial derivative of this with respect to y. Partial derivative of p with respect to x, partial derivative of q with respect to y, and add them. So here's an example. Divergence of x cubed, 2xy to the fifth. Okay, take the partial derivative of this part with respect to x. So derivative is 3x squared. And the partial derivative with this with respect to y. So the 2x stays there and it becomes 5y to the fourth. So it's 10xy to the fourth. And then you just add them like this. An alternative notation, instead of divergence written like this, you could also write this upside down triangle dotted with this. Okay, and that means the same thing. So sometimes write div like this, sometimes I write it like this. What's the deal with this notation? Actually, it's a mathematical pun. It's not supposed to be actually like a mathematically rigorous description of what's going on here. Let me explain. And maybe it's not a mathematical pun. Maybe it's more like a play on words. So here's the idea. This is what the upside down triangle is. It's a vector that's got two components. Partial derivative with respect to x is here. Partial derivative with respect to y is there. Okay. And when you put the gradient, as you know, you could write this instead, right? And if this is a vector and this is a scalar, then we must be doing scalar multiplication, right? Just here's the vector, here's the scalar. Just multiply this both components. Okay, and that's what you get. So it's this times this and this times this. Well, obviously, I hope you realize this is not multiplication, right? It looks like multiplication, but this is actually differentiation. This is how you say the derivative of f, partial derivative of f with respect to x. This is how you say the partial derivative of f with respect to y. This is not multiplication at all, but we use the same notation to write multiplication as we do when we write down derivatives. And this is what I mean by this is a mathematical pun. Um, it's like we write down the same thing, and it can mean two different things. And even though in this case it's clear it means one thing, we're writing it down as if it meant another. Right? That's a play on words. So if this were multiplication, then this would be a perfectly ordinary way to just distribute your scalar into your vector components as for scalar multiplication. But if this is not even multiplication, right? So what's going on here? Well, the point is we define the gradient to be this thing, and this notation here is helping us remember through this play on words how to do it. Likewise, what happens if I take this vector dotted with this vector? Okay, like this. Well, I would take this times this plus this times this and add them. So this times this is this, this times this is this. So partial derivative with respect to x times p. Now, of course, this is not multiplication. This is the partial derivative with respect to x of p. And this is the partial derivative with respect to y of q, not multiplication. But it looks like multiplication, right? So this will help us remember how this formula goes. Okay. So here's how we use it. Okay, you need to take the divergence of this thing dotted with this. Sometimes this is called del. Lots of things are called del in calculus 3. So del dot this vector. Just write this vector here with the partial derivatives inside here. And then this here, and take the dot product. Okay, I'm treating these as if they're numbers. They're of course not numbers, right? So that's why we're not multiplying here. I mean, another way of saying that using more grammar terminologies is I'm treating this as if it's a noun, and it's really a verb. I'm treating it as something that I can, manage. This is like a number that I can do something with. In fact, this is telling me to do something. In this case, partial derivative with respect to x of this. The other thing that this is helping us to do is, this is helping us to remember that this whole thing is supposed to be a scalar. Okay, that is, you're supposed to add this all up like this, because the dot product immediately at this point should get you to remember that we are, adding these things together. We're not just keeping them in components. Since the dot product takes two vector and returns a scalar, this, okay, here's a vector, here's a vector. I mean, obviously this is not really a vector, like I said. This is this thing. It looks like a vector, but it doesn't have numbers in here. It has these derivatives. But if you think of it as a vector, okay, dotted with this vector, well, dot product of two vectors is a scalar, so this is a scalar field. Now, here's the thing. We knew that it was a scalar field way back when I made the definition back here, right? But the point is, this is what's going to help me remember that this is a scalar field. I see this vector, take the dot product, it's a scalar. All right, so what does divergence actually measure? The name divergence might give you a hint, okay? And it's kind of hard to actually see, but I'm going to try here. Here's a vector field P comma Q, and here's what I'm going to imagine. Imagine the entire plane is made up of tiny, tiny little squares, microscopic little squares. I'm going to zoom in, and look at one like here. And here's the idea. When I say partial derivative with respect to x, I mean going from this side to this side. Okay, from this side to this side. Now, let's say I've just focused on this, partial derivative of p with respect to x. If I want to know if this is positive, then that means that p is increasing when I go from this side to this side. But the thing is, p is the x component. That means I don't care about to what extent the vectors point up or down. I just look at whether they're pointing left or right. Okay, the extent to which they're pointing left or right. And what this means is it's increasing. So here I have a p that's negative. The x component of this is negative. Here the p is positive. Well, going from here to here, going from negative to positive, that's an increase. And so this partial derivative is positive. It doesn't have to be that way, though. It could be also going from something small to something big. Okay, that's also positive. Or something very negative to something less negative. That's also going to do this. Well, it's easiest to see here. You see, if you imagine that this is describing how we stretch something. If say you have a rubber sheet, for example, here, and here you're going go this way, this one you're going to pull this way. We're stretching it out. Right? Or another way of thinking about it is you've got two people, one here and one here. This guy's going this way, this guy's going this way. They're moving apart. That's where the word divergence comes from. Similarly here, if there's a rubber sheet and I pull this one a little bit and pull this one a lot, right? Then this is going to move a little, this is going to move a lot, and it's actually going to overall stretch. Or if these are people, this guy's moving this way, this guy's moving this way much faster, then these guys are going to be getting further and further apart. Likewise, we can look at this one. It's the same thing, but in the y direction. This time I'm looking not at p, but I'm looking at q, which is the y component, the extent to which things go up and down. And the same idea here. If this is going to be positive, then that means this is going up and this is going down. Or this is going up a little bit and this is going, say, going up a little bit, this is going up a lot, or something like that. Any one of those possibilities. That's going to be the evidence that the partial derivative of q with respect to y is positive. And the idea is, this is describing kind of a stretching in the y direction. This partial derivative of p with respect to x is describing a stretching in the x direction. You add them together, that's kind of describing a total extent to which these things are stretching out. Here's an example. Here our vector field is x comma 0. Okay, it looks like this. And as you see, the vectors are kind of small here and the horizontal. Here the vectors are getting longer as they get further away from the y-axis. And if you imagine a rubber sheet, and this is describing how it's getting pulled, then it's definitely getting stretched. It's obviously getting stretched in the middle here, but look over here, it's also getting stretched here. This is moving a little, this is moving a lot, and it's also being stretched here. Okay, moving a little bit here, a lot here, it's going to get stretched. In fact, the fact that you take the partial derivative of p with respect to x, that is partial derivative of x with respect to x is 1, partial derivative of this one is 0, add 1 plus 0 is 1. What this says is this is a constant divergence here. Everywhere it's diverging exactly the same. Its divergence is the constant 1. Okay. Likewise here, partial derivative of p with respect to x is 0, partial derivative of q with respect to y is 1, add them up and get 1. Okay, so this one is looking at this side, this one is looking at this side, stretching in the x direction, stretching in the y direction, right? Either one will give us divergence. Okay. You can have both. This one has x, y, this is this vector field like this. Partial derivative of p with respect to x is 1, partial derivative of q with respect to y is 1. 1 plus 1 is equal to 2. So this is a little bit of both kinds of stretching. Okay, and that's the divergence. Divergence is constant too. In the center, it's obviously divergence is positive, but out here it's also positive. Things are moving faster on the outskirts than they are on the middle part of this diagram. And it turns out it's constant again for this. Everywhere here has constant divergence. Divergence 2. If I reverse all the arrows and go this way, negative x comma negative y, take the partial derivative of p with respect to x is negative 1, q with respect to y is negative 1. Negative 1 plus negative 1 is negative 2. And all these arrows turn backward, and they're all heading toward the center here. Things are getting scrunched at a constant rate everywhere. That's divergence of -2. Here are some other interesting examples. Here's x comma -y. I've just combined two different ones here. Here, partial derivative of p with respect to x is 1. Partial derivative of q with respect to y is -1. Add 1 plus -1, you get 0. And here, it's a little hard to think of it in terms of stretching the rubber sheet. I mean, the rubber sheet does get, well, overall it gets stretched, but it gets stretched in one direction and scrunched in the other direction, and overall it doesn't get scrunched at all. Maybe easier is to think of people, and as people kind of head toward each other like this and they kind of split off in this direction, it turns out people are not getting any closer together. Or another way of thinking about it is you're going to shoot a water hose this way and a water hose this way. Remember, this is in 2 dimensions, so water can't just go up out of the page, but water hits and it's going to get deflected in these directions and shoot out this way and this way. Water is actually a good example because water doesn't like to scrunch up very much. I mean, not as much as a gas. A gas is fine getting bunched up, but liquids, especially things like water, they're not very good at getting squished. They don't like that very much. And so, I mean, they can do it, but it takes quite a lot of effort to make them compress or stretch out. And so, under ordinary circumstances, water flow is going to have divergence approximately 0, very small, right? And that's, you can imagine water doing exactly this. Here's another one. Okay, partial derivative of p with respect to x is, well, partial derivative of negative y with respect to x is 0, right? There's no x here. And partial derivative of q with respect to y here, that's also 0. And so when I add them, I'm going to get 0. This is our favorite little swirly vector field. This is not the one that was our counterexample last time. That one had divided by x squared plus y squared on both of these things. This is the original one that we worked with a while ago, right? Where it's just swirling around. It's not even pretending to be like q sub x being p sub y or anything like that. No, that's not what's happening here. So what's going on here? Well, again, nothing is really getting compressed, right, or stretched out. It's just spinning. All right. So that's divergence. In 3 dimensions, okay, I don't have pictures for you in 3 dimensions. They're really hard to draw these, and I didn't have a lot of time to put these together. So sorry, I don't have 3-dimensional things. 3-dimensional things on the computer are a little hard to see anyway. But here we go. This is PQR. Okay, those are the 3 components of our vector field. They're all functions of x, y, and z. And the divergence means I take the partial derivative of this with respect to x, partial derivative of this with respect to y, partial derivative of this with respect to z, and add them all together. Okay? This is just by straight analogy from the 2D case. And again, this del is going to be this vector with partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z inside them. Again, this is a little bit nonsense because what does this mean? It's not clear. But if I write it down and put a dot product here and just don't worry about it, this actually works. Take the partial derivative of this with respect to x. Okay, this one doesn't matter because it doesn't have x, but this one is 3x squared y. That's what goes here. Partial derivative with respect to y of this thing. There's no y's here, so this is a constant, and the partial derivative of that is 0. And then here, partial derivative of this with respect to z. Okay, and that's x squared y squared times 2z. And there we go. So this is how we do divergence in 3 dimensions. The picture is kind of similar. Okay, it's now 3-dimensional vectors everywhere in 3-dimensional space, and it's trying to describe to what extent things are getting further apart from each other. That's divergence. So on to curl. Okay, so curl looks like this. So curl, by the way, only works in 3 dimensions. Okay, there is no curl in any other dimension. And curl of a 3-dimensional vector like this is this formula. This partial derivative of r with respect to y minus partial derivative of q with respect to z. That's the first component. This is the second component. This is the third component. Okay, so this is the curl. And again, there is a use of this mathematical pun. This del cross PQR. Okay, see what happens. You take the cross product, you take this determinant, ijk, partial derivative with respect to x, partial derivative with respect to y, partial derivative with respect to z. Those are the components of this symbol. And then p, q, and r get put in here. Now, of course, this gets broken down into this time something times I plus something times, or minus something times j plus something times k. These somethings are 2 by 2 determinants. This times this minus this times this. So this times this is partial derivative with respect to y of r. Okay, so that's not times, right? It's partial derivative with respect to y of r and partial derivative with respect to z of q, but I subtract them. And similarly here, we get these things and these things. And you see that we get the same thing. Partial derivative of r with respect to y, partial derivative of q with respect to z, subtract. Now remember there's a minus sign here, so we got to distribute the minus sign before we do anything. And this is going to make this positive and this negative. So partial derivative of p with respect to z minus partial derivative of r with respect to x, pz minus rx. And then the z component is going to be this, partial derivative of q with respect to x minus partial derivative of p with respect to y. There it is, just like so. So like I said, what I've written down here, it's not clear what it means when I write it like this, but it's way easier to remember this than to remember this. I mean, it's not too hard to remember that it kind of looks like this, but it's often hard to remember which terms go where. And this description makes it clear. All right, so let's try it. Curl of this thing, okay, we just put ijk, partial derivatives with respect to x, y, and z here, and x squared, x, y, z, and x cubed here, and break it up into these pieces, this times I minus this times j plus this times k. Partial derivative of this x cubed with respect to y, that's 0. Partial derivative with respect to z of x, y, z is xy, and you subtract. Minus, or that's the I component, minus, and now you take the partial derivative of x, which is of x cubed is 3x squared, and partial derivative with respect to z of x squared is 0. So subtract those, and then similarly partial derivative with respect to x here, that's yz, and minus partial derivative here is 0, and just put them all together, negative xy, negative 3x squared, and yz, like so. And that's the curl. Curl of this vector field is that vector field. Okay, so that's pretty straightforward, if a bit long in process, but by now you're happy doing cross products, so I think so. This shouldn't take too long for you to do. Since the cross product takes two 3D vectors and returns a 3D vector, okay, we remember that the cross product of these things, this looks like a vector, that certainly is a vector. Take the cross product of this is a 3D vector field. I say 3D, I emphasize 3D here, this only works in 3 dimensions. All right, let's see if we can understand what the curl is. All right, the curl is going to be kind of hard to explain. Partly the reason is it's a 3-dimensional vector, and it's kind of hard to explain a 3-dimensional vector. So we're just going to look at this one piece here, the z component, okay? And we're going to try to see if we can understand what's going on there. We've got partial derivative of q with respect to x, and we've got negative partial derivative of p with respect to y. And if this is going to contribute positively to this, then partial derivative of q with respect to x should be positive, and partial derivative of p with respect to y should be negative, so that negative is going to be positive. Either way, one of these kinds of things is going to contribute to making this bigger. So let's look at these pieces. Q, partial derivative of q with respect to x. That means I'm looking at the left side to the right side. And q is the vertical part of this. Okay, it's the y part. So if it goes from negative to positive, then that's going to contribute to this. Or slightly positive to more positive, that'll also do. And same with negative, you know how that goes. Partial derivative of p with respect to y being negative, that means it starts as positive and ends as negative, or, you know, again, very large to not as large, etc. If you look at what's going on in this case, all of these vectors are going to be contributing to a sense that this whole thing is spinning. This is maybe suggested by the name here, curl. Things are curling around. Now, here's the thing. Curl is not a number, right? It's a vector, and this is just the z component. And this is the z component is describing what's going on, but I have to look at p and q, which are the x and y components, and I have to ask how they're changing in x and y. So basically, I'm just looking at the plane perpendicular to z, and seeing what's going on in this plane to tell you what the z component is of this vector. So the contributions in the plane are going to be to the component of this vector that's pointing perpendicular to that plane. All right, let's look at some examples. Okay, here is negative x comma y comma 0. Okay, so it's kind of like this, except of course this is two-dimensional, right? It's really hard to draw these in 3 dimensions, so I'm just using our imagination here. This is the xy plane, but imagine this is actually sitting inside 3 dimensions, and at every level of z, you get the same thing. So you've got basically this huge like hurricane at all levels of z, and it's swirling around the z-axis. And we take the partial derivative of, well, all of this stuff is partial derivative of q with respect to x and partial derivative of p with respect to y are the ones we're really going to focus on. You notice that I don't have these vectors pointing up or down at all. This is 0 here. That means r is 0. So all of these, everywhere I see r, it's going to be 0. And also, this is not changing with respect to z. These do not depend on z. So partial derivative with respect to z of anything is going to be 0. So this is guaranteed to be 0. This is guaranteed to be 0. That's how I got these two zeros here. And this one, partial derivative of q with respect to x, we just have to calculate. This is q. Partial derivative of this with respect to x is 1. Minus partial derivative of this with respect to y, which is negative 1. So 1 minus negative 1, 1 plus 1 is 2. So that's what this z component is. Okay. And so when there's this swirling around on all levels, the idea is the curl is pointing on the z axis. It's a little hard to do on the computer screen because I want a three-dimensional picture here, but it's pointing. So remember, this is lying flat on. I don't know how you've got your tablet or your phone or your laptop or whatever. This is x. This is y. Z is perpendicular to both of these things, and that's the direction that the curl is pointing in. So when it's swirling around this way, it's pointing in something that is basically along the axis of the spinning. All right, here's one where it's got x, y, 0. Partial derivative, well, this is partial derivative of r with respect to y. There's r is going to be 0. So all these r terms are going to be 0. And none of these depend on z. So again, this is going to be 0. So these are going to be 0 and 0. And here, q sub x, that's partial derivative of q with respect to x, partial derivative of y with respect to x is 0. And say minus partial derivative of this with respect to y, that's again 0. So again, you get 0, 0, 0. This one has no curl. So I remember actually that this is not, of course, this is 2-dimensional. Curl has to be on 3 dimensionals. Again, copies of this at every level. These are all emanating from the z-axis. And we get this. This is something that has no curl anywhere. Okay? There's no spinning around. What is curl? So basically, the idea is when f is seen as kind of swirling around an axis, it's not exactly that any more than divergence is. It's things are moving away from a point. It's kind of this overall sense of swirling. So here's what I do. I imagine like a windmill, and I ask myself, would the windmill spin, right, in this thing? Curl of f is always going to point along the axis of that swirling. Okay, it's got a right-hand rule to it. Okay, so that if you got your right hand and you point your fingers along the swirl, your thumb will point in the direction of curl of f. And one way to make sure that you've got this right, just try out this example here. Okay. Remember, this is x, this is y. Use the right-hand rule to figure out where z is. It's pointing out of the computer screen. And this swirling, okay, if you imagine your right hand, put your right hand around and you point your fingers around the swirl, your thumb will point again toward you, or that is perpendicular to the computer screen toward you. So that's how the curl of f points. It points along the axis in the right-hand rule. The magnitude measures the amount of swirling. So there's a lot of activity then it's going to be a really long vector. If it's a really calm swirling, then it's a very small vector. All right, now time for you to try it. Here is a three-dimensional vector field. Find the divergence and curl. Go ahead, pause the video and do this one, and then unpause it to find the answer. All right, are you back? Find the divergence. Divergence should be this. Partial derivative of this with respect to x is 1. Partial derivative of this with respect to y is going to give you x, sorry, 2xy, and plus z, that's this. And the partial derivative of this with respect to z is x. And you add them all together, we get this. And curl, we get this. So here's how we set it up. And we're going to get negative y, negative z, and y squared. Okay, so that's partial derivative of this with respect to y is 0. Partial derivative of this with respect to z is y subtract. Anyway, this is how we do the curl. All right, ready to try another one? Here's a two-dimensional vector field. Find the divergence of this. And ready, go. All right, did you get it? If not, you pause it more. All right, here it is. Partial derivative of this with respect to x is sine y. Partial derivative of this with respect to y is natural log of x times x to the y. So remember, that's how we deal with derivatives when y is the variable. Okay, this is an exponential function, and take the derivative of that. You get this. Okay. Why didn't I ask to find the divergence and the curl? Okay, you should be shouting at your computer screen the answer here. It's because the curl is not defined for two-dimensional vectors. The curl is only defined for three-dimensional vectors. But actually, we did do something like it, actually. The z component of the curl. So here's the thing. Two-dimensional vectors in the plane, right, like this one would be, could be stuck into 3 dimensions. Here's what you do. You just put comma 0 here as your third component, okay, and stick it in the plane and then make it not depend on z at all. And then curl f, the z component will be q sub x minus p sub y. Well, never mind the gymnastics of actually sticking this inside 3-dimensional space. This certainly makes sense. Q sub x minus p sub y. And I can certainly take the partial derivative of this with respect to x, which is y x to the y minus 1, minus the partial derivative of this with respect to y, which is x cosine y, and subtract like that. Okay? And this is not a vector. Okay? This is a scalar. This is a kind of a funny kind of object, right? So this is what would happen if you took this, stuck it inside 3 dimensions, and you have to do 2 different things. First of all, it has to have a z component, which you're going to define to be 0. And the second thing is we're going to ask, how does it depend on z? And the answer is it's not. It's going to be constant in z. And so you're going to get the same vector field on every level of z. Okay. And when I do that, and I take the curl will only have a component in the z direction, and it's going to be qx minus py, and that's what we're talking about here. Okay, so this is, it's not really a two-dimensional version of curl. It's kind of like that, except it's giving me a scalar, and that's what this is. I prefer to think of it as the z component of the curl if you're sticking inside 3 dimensions. Next time, we're going to talk about properties of divergence, gradient, and curl. We're going to talk about Green's theorem for and the divergence and the curl. And we're going to talk about Clairaut's condition for 3-dimensional vector field. So remember, when we were trying to describe whether a vector field is a conservative vector field, there was a lot to be said about it, but all I was dealing with was in 2 dimensions. The 3-dimensional version is more complicated, and that's what we're going to have to also discuss. So you should be able to actually do a lot of the problems on the homework. Maybe not every single one, but certainly all the computational ones should be fine. Some of these other topics will be covered next time.